didn't cost so much money. Doing okay so far. Checkity check, check, check. Any second now. And we're live. All right. Hey, how you doing out there? Happy Sunday. I am back doing LeetCode. A little late today. Slept in, had some errands to run as best I could. And so here we are now. Now, I had a little bit of trouble with yesterday's problem with a tree. So I was thinking about maybe streaming just some tree problems later. Maybe I'll try to do like 10 tree problems or something just to kind of get my head back in that game. So watch out. I might do that over on Twitch though. I don't know. Still mulling some things over. But anyway, let's get to it. Last stone weight. So we have a collection of stones, and each stone has a positive integer weight. Each turn, we choose the two heaviest stones and smash them together. Suppose these stones have x and y, where x is less than or equal to y. And the result of the smash is, if they are both equal, then they're both totally destroyed. If x is not equal to y, then x is destroyed, and y has a new weight. Okay. Excuse me. At the end, there's at most one stone left. Return the weight of this stone, or 0 if there are no stones left. Okay. So, weird story, but not a hard problem. So let's walk through a potential solution, and maybe we can figure out some ways to kind of run this in a decent amount of time. Because right now, the number of operations we have to run is variable, and it could end up being kind of weird if we have a lot of really big stones, maybe. So I'm going to think about that. So if we've got this collection here, first pass, we're going to take 8 and 7, smash them together, we'll get 1. Then we got to look at the next two biggest, which are going to be 4 and 2. Is that right? Oh yeah, we got it right down here. And then we end up with 2 and a bunch of 1s. And at the point we get to a bunch of 1s, and things clean up rather quickly after that. So, my first inclination is a recursive problem, but I typically don't like recursive solutions because they end up potentially taking up a lot of memory. You get a potentially stack overflow. And even if you don't have a stack overflow, just depending on how big your data set is, you can just have a lot of memory just kind of out there sitting. So what is the actual result of this is either the weight of the last stone or 0 if there are none left. So I got a couple ideas. I mean, one, if we just sorted this thing right out of the gate, we would have things sorted by weight. The gross thing about that is that we'd have to kind of insert back into that sorted list or array. And inserting into arrays is nasty. It's a O of N operation because you have to bump everything to the right of it. Also, plugging things out of arrays all the time is also pretty nasty because you have to shift everything to the left. So an array is not a great data structure for doing this sort of thing. With shifting positions and whatnot. I'm kind of wondering about a heap structure. Heaps let me quickly pop the last item off, and it would be easy to pick, basically. So I would just pick the top 2 off of it, and inserting is also really easy. And so I do think that a heap is the right answer here. So now at this point I have to figure out, is looking up the algorithm for a heap cheating or not? Can I make a heap from memory? I don't know. What do you think out there? Any suggestions? Should we try to Google for the algorithm for the heap, or just try to figure it out? I'll tell you what, since that's pretty much the entirety of the algorithm is the heap, I will not look it up. I'm just going to try and do a min heap from memory. So wish me luck. And we'll do it in an array. We'll do it in an object that has an array. Let's see, items, sure. And heap will have operations like add, which will take an item. And thinking here, there's basically two main functions of a heap. There's percolate up, and I think that's it actually. I think that's, is that percolate up or percolate down? Dang it. I'm just gonna call it percolate now. I think we're gonna end up doing both. I think we need a percolate up and a percolate down. So it's coming back to me. And I'll go ahead and call this a min heap. So this is a good data structure to know because it comes up in problems like this pretty often. So I really ought to figure this sort of stuff out. So when it comes to adding is super easy. So basically we just add the item wherever at the end, and then the trick is then we call percolate up, and we probably have to give it the index of the item we just pushed. I think that makes sense to me. All right, and so just a little refresher course, mostly for me. The deal with the heap is the first item is the root. That's going to be, in this case, the least. So actually I want a max heap. So it'll be our biggest item. And this will be root left. This will be root right. And then the next element will be like the root left, and the root left, right, and so on. And so you can predict the position of any item, or given an index, you can always tell what it is, because the deal with a heap is that it always fills in left to right. So this array will always be in the appropriate order for the tree, which is pretty cool. And the trick here is whenever you add a new item, you have to percolate up, which means essentially doing a couple swaps. So I'm going to go ahead and kind of create a max heap here. So 10, and I'll make it with a child to the left of 5, child to the right of 6. And what we're going to do is we're going to push a new bigger item on. So we'll push 20. So what we do here is first we add to the end of the array, boom, and then we percolate up, where we say, hey, you get compared with your parent, 5. Which of you is bigger? Okay, 20 and 5 swap. And then we're gonna look at the 10 and 20, swap again, and we're done. So all percolate up is going to do is take in an index, and it will say if items at parent index, which we're gonna have to look this up, or rather we're gonna have to figure this out. If the items at the parent index is less than, and only less than, the items at the index we're looking at, then we need to swap. Meaning that items at parent index equals, oops, we'll need a temp variable as well. Equals that. Okay, and then items at index will become our temp. And if we do that swap, and only if we do that swap, we need to call Percolate up again and pass it the parent index. And we'll compare these guys. So that's it for Percolate up. We do have to watch out. There are two other things. We have to figure out the parent index, which is going to be a little tiny math formula. And then we have to not check if the parent index is like basically -1. So if we try to check is less than 0, then we can just return, we're done. All right, so the parent index, so given this this one, right, that's not a good one to look at. Let's look at this guy. So its parent, oh gosh, let's draw this tree out a little more formally because I'm going to get confused here. Trying to figure out the mathematical formula in a min or max heap. Sure. And they always go left to right. So sure. So if I want to know whose parent this is, and to write this out in an array, it would be 10, 5, 6, 3, 1. So I want to know one's parent. It's going to be my index. Let's call it I'll just call it index. Minus why am I even trying to think this out? Why am I trying to do it this way? Let's slow it down. So I have 5. I'm going to have some function that takes in 5 and returns, or sorry, not 5. That's going to be index 1, and it needs to return 0. I've got a function that takes in 2 and equals 0. I've got a function that takes in 3 and it takes in 1. So and here I'm looking at the 4th item, 4, and its parent is also equal to 1. And the 5th item now your parent is 0. Your parent, you have no parent. Your parent 0. Your parent is 0. Your parent is 1. Your parent is 1. Okay. F0 does not have a real parent. Okay. So I think it's index divided by 2 minus 1. So it's going to be math.floor of that. So does this work? So if I take in index 1, so 1 divided by 2, and it's going to be 0.5. So we're going to floor that to 0. Okay, if I take in 2, 2 divided by 2 is 1. I think it is minus 1. All right, let's try that function of 3. 3 divided by 2 is going to be 1.5. So 1. It's ceiling. All right, try that again. So function of 1 is going to be 0.5. So it's 1 minus 1 is 0. So that checks out. What about 2? 2 divided by 2 is 1 minus 1 is 0. Check. 3 divided by 2 is 1.5. Round up to 2. 2 is 1. So I think this is it. And if not, we'll find out. All right, so that's it for Percolate up. This will always be good. Okay. Now we also need to handle Percolate down. All right, and the deal with Percolate down is this should really be private, so I'll call this one remove max, or they have another word for it. It's like pick or something. Pluck, I think, is the term you usually hear with heaps. I'm also kind of curious, like, do you guys have like the heap algorithm memorized? Is this something I should be worried that I'm not ready to just bust out very easily? I guess that's why I'm doing these problems, right? I want to be able to bust this stuff out very easily. Oh my gosh, look at the way I'm not writing this stuff appropriately. All right. So the deal with pluck is I'm going to return the top element. That's the easy part. Let's see. So const value, I'll call this max value. That's the whole kind of value of this heap, so I can cheaply get and cheaply maintain either a maximum or minimum value for a set. So it's always going to be items at 0 at the first position. At this point though, I've basically got an empty spot in my array, and so I need to do a series of swaps in order to get my heap back into shape. So in this example up here, what I did is I'm taking the 10 out. And so what we need to do is typically known as a percolate down operation. And we'll start at 0. And the way percolate down works is pretty similar to percolate up. Percolate down equals index. And what we do is we are going to get our left value. We'll figure that out in a sec. And we'll get our right value. And then basically, if left is greater than right, then what we do is we basically update our current position. So items at left, items at my index equals left. Otherwise it equals right. Remember, with percolate down, we always have an empty spot. So there's never a case where we don't do one or the other. So let me rewrite this a little bit. So if left is greater than right, then we'll pop in the left value. Otherwise, we'll do the right. If they're equal, then it doesn't matter. That's what I like about heaps. I like that they're kind of loosey-goosey with that sort of thing. And the deal is that they always know the maximum value, and we always know that either the left or the right is going to be the next max. And then we just percolate down to get things straight. So we will have to figure that out. And then at that point, oh geez, I do need to maintain which one we did. So if left is greater than right, I'm going to have to rearrange this a little bit. Then we'll go left. But then also, let's change this to be left index and right index. So items at left index is greater than items at right index. Then items at my current position is equal to my items at my left index. But then I need to call percolate down again, looking at that item, because now I've created a hole. All right, so percolate down is going to be at left index. All right, and then our else, we're basically going to do the same thing except for the right index. Right index. Okay, so there is a max heap. I feel pretty good that I remembered it, surprisingly. I feel less secure about my JavaScript here. So I'm definitely mixing up my language. It's all right, it's not hard to fix. items is weird. I don't think I can just use it like that, but we'll see. First I want to go ahead and get the left and right indexes worked out. And it's basically going to be the opposite of this formula. So if we kind of take this formula, math dots, and I think in JavaScript it's actually seal, not ceiling. Say ours is index divided by 2 minus 1 equals child. We'll call this parent. Then we want to basically rewrite this equation in terms of parent. So I think this is just going to be kind of straight up old school math. Seal divided by 2. I don't really know how to do that really. So I'm just going to ignore that math.ceiling for now. We'll figure it out. All right, times both sides by 2. So your parent equals 2 times the child index plus 1. All right, so we can test that out. So if I wait, I think I wrote these things backwards. Child equals 2 times the parent. So I have a left and a right though, so we'll say left equals that one, and right should always be just one more greater than it. So let's see how that works. So if I'm at position 0, then I should expect to get a 1 and a 2 for my 2 children. Do we do that? So parent plus 1, 1 times 2. Okay, I can already tell that I'm wrong. I'm off by 1. Then we add 1 to it. So what did I do wrong there? 2 times the parent. I think I might have done this wrong. Alright, let's try that again. So my parent is 0, I expect to get 1 and 2. 2 times 0, 0 plus 1, 2 times 2 plus 2. Okay, so that worked for my root. Let's try for the left. So for my left item, the parent is 1, check. The answer that I want to get is 0, 1, 2, 3, and 4. Write that down. So I want 3 and 4. All right, so if you're just joining, we're basically, we've got a problem here. It's kind of funky, but I think the best way to solve it is basically with a Max-Heap. So I'm just kind of challenging myself to do a Max-Heap for memory, and it's gone pretty well, just having to struggle a little bit with the math formulas for finding the parents out of an array, which is like the normal, or JavaScript array, so a vector. It's kind of like the standard way of doing a heap because of the way they kind of fill in from left to right. So it just fits really nicely with that. And then I've got the 2 major components, percolate up, percolate down. I feel pretty good about how I did those, how I remembered those and programmed them. I am just double checking the math here, and then we should be able to solve this problem really easily. Also, if you remember heaps better than I do and have any advice for me, I would love to hear it, because my algebra skills are super rusty. So we have 1, 2 times 1 plus 1 is 3. 2 times 1, 2 plus 2 is 4. So I think this is good. So here we go. So 2 times my index plus 1, and 2 times index plus 2 for the right child. Now I do have to make sure that I don't go out of bounds here. So if my left index is greater than items.length, that means I have no left child, then I can just return we're done. If, however, the right index is greater than items.length. I don't think that should ever happen. I do have to decide whether to swap or not. Is that right? Trying to figure out if I ever have to worry about this case. This handles if we don't have a left, we don't have anything. If we don't have a right, yeah, I think that's valid. We just have to make sure that if we don't have a right, then we only do the left swap. So there we go. That's it. I think that's it for the Max-Heap. And I don't have a good way of testing this. Particularly worried about using the items like this up here and also down here. I really should have written like a JavaScript class or something, but frankly, I don't know how to do that without some IDE help because I just don't do that sort of thing very often. So, okay. It doesn't seem to want me to enter this into the console. I was just hoping to kind of test it out. Oh, well, I mean, this will do it. It's going to be pretty embarrassing if I have to look up how to do like objects in JavaScript, but I was able to remember how to do a heap. It's one I do all the time and one I never do. Let's see, Max-Heap dot items. What do we got? Okay. So that looks good. So if I do Max-Heap dot add, give it a 10. Items is not defined. Okay, so I think the deal here is that a cheap way to solve this is basically just to prepend Max-Heap anywhere do items, which is annoying, but not the end of the world. Definitely annoying. And I could have solved this in other ways, but I don't want to. Items, jeez. This IDE is not so great for find replaces. It's almost like they didn't expect anyone to do anything like this. Crazy talk. Oh my gosh. I'm like 2 seconds away from just taking this all over to code and doing a replace there. Alright, hopefully nothing embarrassing up there. Alright. Let's do a quick regex here. If I have a word boundary, no. Oh my gosh. I'm just going to do this. It's kind of awkward because I already kind of half started replacing it. Max-Heap dot items. If you want to paste me that, though, I would take it. I guess I could just do this. Set replace in selection. Yeah, so that would have been the fastest way to do it, I guess. All right. Clear that again. I'm going to change this to a var just so I can redefine it. It's doing that thing again. What the heck? Missing blank after property ID. Oh, I know I got a Max-Heap my percolates too. Percolate up, percolate down. Okay. You should have one for percolate up. Percolate down needs to look at 2. All right. gosh. Missing colon after property ID. Oh geez, it's all supposed to be objects. Man, I hope that I have this solution right and that I didn't just waste a bunch of time creating a Max-Heap for nothing. Redeclaration. Oh man. Max-Heap dot items. Okay, so Max-Heap dot add should go into items dot the first spot. Okay, good. So Max-Heap dot add a 5, 6, and sure 7. Okay. Items is not defined, so I missed somewhere. There it is. And that was happening on a percolate up, which is good. Missing other items? Don't think so. Okay, cool. I think we got this. Let's find out. Let's see. I did redefine this thing, so I kind of want to just add some other cheater things in here. We'll do 10, 5, 6 and 7. Okay. Just testing our heap here. All right, I got all those. Okay. Oh, and we can actually see that it worked already. So it's swapped that 7 and that 5. So now if we do Max-Heap.pluck, it should remove that 10. And what else? It should put the 7 into the first position, and it should move that 5 up. Okay, 2 is not a function. What happened there? This happened on our pluck. Max-Heap.items, check. Percolate down. Starting at the root, fine. Oh, look at that. 2 times. Okay, one more time. This is it. That is not it. Look, I left a parenthesis somewhere. Missing a parenthesis after a condition. Oh yeah, look at that. I don't know what happened there. Okay. Alright, let's try this again. We're so close. Thanks for sticking it through. Oh, let me rerun these commands. Okay, we Max-Heap dot items. We'll just make sure that that still worked. Yep, so we can see we've got 7 in the second position, which is good. Pluck. Oops, needs to return 10. I don't know if I ever told it to return the value. I guess not. But if we look at the items, we should see if the hard part worked. And yeah, it did. It moved that 5 up. Now, there is a problem there because I didn't remove that 5 at the end there. So that's unfortunate. So almost got it. Also, the pluck needs to return that max value. Okay, so one problem down. So percolate down. If I have no left children and no right children, then what does that mean? How do I know when to stop, basically? Right now, this is the only case I've got. If the left index is greater than this, then We return, which is fine, but we also need to essentially null this item out. Well, you know what? A cheap way to do this would be after we percolate down, we just remove the last item from the array, which we could just do with a Max-Heap dot pop, and we don't need it because we want the first item. But that's it. All right, one more time in the console. This is going to do it. And then we can actually solve the problem, I hope. Max-Heap dot items looks good. If I pluck the Max-Heap, and I should get an answer of 10, and I want to see that 7 move up. So I want the final state of the array to be 7, 5, 6. Oh my god. Thank you so much for your patience. This is such an awkward way to work in the console here. I'll go ahead and add this item in here too, so I don't have to keep doing it. So, hey, look at that. So we got the right answer. So now the question is if the right items are correct, and they are. So cool. So we just did a Max-Heap for memory. Yay. So with this, we should be able to come back to this problem, and I'm going to reread it because it's been a while. Took me, I don't know, let's see, 30 minutes to remember how to do a Max-Heap. So thank God I'm not in an interview. All right, so the problem that we were originally trying to solve is a weird problem about stone weights. So we have a collection of stones. Each stone has a positive weight. Each turn, we take the 2 heaviest and we smash them together. If they're the same weight, they're both destroyed. If they're not the same weight, then we subtract the smaller one from the bigger one, and then re-add that weight to our collection. So with our heap, basically, all we have to do is say stones dot for each. We're going to we'll call it stone, sure. We're going to add to our Max-Heap. Okay, and we'll move this Max-Heap above. Okay, and I'm going to keep an eye on our runtime here. So this just made us O of n because I'm going through each item and doing an operation here, adding it to the heap. Now, we also have some overhead for this heap, and I believe that's going to be the log of n. We do have to do some swaps where the maximum number of swaps is the height of the tree. This is a binary tree, so it's log base 2. So right now, just off the bat, without doing any work, we're at O of n log n, which is not great. So this is not going to be an award-winning solution. But it might be the best. I'll have to think about that a little bit and think if we can think of a theoretical case where we only have to look at our inputs once. But I kind of doubt it. All right. So this fills up our Max-Heap. Check. So what do we need to do now? Basically, we'll say, we'll make a new function called smash. And it will, do you want to take the whole heap or just 2 stones? I will take it, have it take the whole heap, sure, which I guess is a global, so screw it. Speaking of which, we might run into some troubles when they rerun the tests because this is a const. So let me go ahead and just do that. Should do an iffy and just have it always. Yeah, let's do that. We'll say let create Max-Heap equal, or screw it, do it the old way. Function create Max-Heap, and all it does is just return this thing. All right, so now this thing will be appropriately scoped, and we can create multiple of them. So that's all good. Okay, mo proper. Now we do have to create our Max-Heap. Say const Max-Heap equals create Max-Heap. And we go through and fill it up. All right, now what we can do is basically smash. So say function smash. And what we'll do is take in a Max-Heap, and if Max-Heap dot length, dot items dot length equals 1, then we're going to return 1. Okay, and let me just make sure I read this. So at the end, if there's at most 1 stone left, at most, oh, return the weight of the stone. Okay. Return Max-Heap at the items at 0. Another case we need to watch out for is if Max-Heap.items.length equals 0, in which case we return 0. Okay, and now if it's greater than 1, then our job is easy. We say left equals Max-Heap.pluck. That's always going to be our biggest item. Our right is going to be, they could be equal, but left is always guaranteed to be easiest. Hi, New Tech Tricks, how you doing? So we'll get right is going to be our second biggest unless they're equal. And then we're just going to smash them together. So what we're going to do is Max-Heap is going to add the result of left minus right. That's not totally true. I don't want it to add a 0. So if left is not equal to right, then we'll add a new stone. That's the difference. Okay, so now the question is, who should call this function again? I don't have to do it recursively. Recursively, this is set up very easily where I could just kind of keep smashing until it's done. But I also could just iterate, which is going to be better on the memory. Yeah, so maybe we'll do that. Return null. How can you get started on LeetCode? So I'm using a free account on LeetCode. You basically just go and I'll open up in a different window and show you. It's super easy. Do incognito, so get a brand new session. So what I'm doing is working through these problems, and they're all technically easy, but I think they're pretty tough for easy problems. You are going to have to sign in first. I'm already signed in, so it's going to be weird. I don't want to log out, but once you sign in, you'll see all over the place. They're doing this everywhere. You can just click on 30-day LeetCoding challenge, and after you log in, you'll see there are a bunch of problems. You have to log in to see. I'll show you what it looks like afterwards, but there's going to be like a whole bunch of problems here. I think this is the 12th one, and they're all pretty groovy. And the way I'm solving this one is not beginner friendly. I'm using kind of a moderately advanced data structure just because I thought it would fit well, and it's been a while since I did one. But there's other ways to solve it. But if you're like brand new to programming, then I don't know if LeetCode is a great way to really truly get started. I think tutorials are probably better. So this stuff is definitely kind of testing some advanced knowledge, I would say, intermediate to advanced, like even easies. Does that answer the question? Let's see, where were we? So we had the left and the right, and I was trying to decide what to do about this. And so what I might do is is basically just in our smash, I'll return null. So if I return null, then that's kind of a signal to me to say that, hey, there's still work to do. So what we'll do here is do something awkward like result equal null while basically do a do loop, and we'll say smash Max-Heap while result equals null, and then I do have to actually save the result of smash. All right, well, yeah, I mean, I think LeetCode is an amazing way to start. Yeah, I'll open this up in a new tab and just kind of see how it goes. So if you come into here, you can actually sort by difficulty and just go easy. And then basically you can see kind of some acceptance rates. Oh yeah, sure. Is that any better? Maybe even bigger. So I filtered for difficulty, I think. Yeah. But then you can sort by acceptance. And so the sorting by acceptance is a good way to find ones where people have had an easier time with it. So you can see like right here, you know, we're looking at like ID number 1378. So there are a literal ton of easy problems. Like, it's looking like 5+ pages of 50. So I mean, just tons. And starting with these high acceptance ones is a great way to find problems that are going to be more straightforward and not so tricky. So great for kind of being new at this sort of thing. And I think you'll find after you start doing some problems like this, like do maybe like 10 or so, that it's going to be a lot easier for you. And I'll increase the font size over here too. So I don't know how to get rid of this window here. I'm kind of, the challenge is kind of weird. Oh, there we go. Well, that helps a little bit. So it's kind of not easy to see. Dang. All right, where were we? So yeah, we were just doing the doing this, and then at the end we returned the result. And I think that's it for this problem. The chances of me typing this right the first time, no typos, and any of the new code I wrote was very low. Higher acceptance doesn't necessarily mean easier, but it does mean a higher percentage of people have completed it. So it's, I'll say, a high correlation. It's not going to be 100%, but it's a pretty good guide. It's the best way I know to find good problems, like straightforward, easier problems. Line 68, I've got a return, which it doesn't like. I missed a parenthesis. Let's try this again. The button near previous. Right there. Hey, awesome, man. Thank you. Whoa. Okay, I'll make it bigger and then hide it. Awesome. Well, I learned something new. Thank you. I got another error. Max-Heap is not defined. Okay. Max-Heap.items.push. Okay. And this is a problem with how I did some funky stuff here. So basically I need to set a Max-Heap here. And then I need to return this whole thing. So a heap is a great data structure to know because it's perfect for finding minimums. And so it made my actual problem, like work I had to do for this, pretty minimal. But overall, I have kind of a hard time with this problem being considered an easy. We'll take it the the other solutions that other people have done to see if they came up with some more straightforward stuff that didn't do so much funky stuff. All right, cool. We got the right answer on this sample problem. No, I got the exact wrong answer. So that's not good. So we'll add some logging in here. Say log. Say, what do we want to say here? These will be the two that we're smashing. Left and right. Let's see, const new stone equals left minus right. And then that gets its makes it easy for us to log. Adding new stone for that. All right. Is there anything else we need to see? I guess every time I come into Smash, I could just print out the whole list. Max-Heap.items. All right. So we should have much better information, and hopefully this is just some minor problem here. Okay, so in this case, smashed 8 and 7, which is right. We added a new stone for 1. Check. And then we exited. So the problem wasn't with the smash. We added a new stone, and we returned null. And null got set to the result of smash, and still we exited. Yeah, I really miss doing a debugger, having a debugger, Ryan. I totally hear you. I think that would be nice. Maybe for future problems, I'll start doing in code just because why not, right? I mean, I've already got it open right here. How'd you like yesterday's problem? It definitely threw me through a loop. This problem I knew how to solve, you know, theoretically, assuming I can get the right answer here pretty quickly, but it's just taken me forever to type it out because I had to remember how to do a heap. Which is all that garbage up there. Oh, that was weird. Okay, so we smashed left and right. We added new stone. So that all worked, and I returned null, and that was okay. It just, this part didn't work. Oh, look at that, man. Look at that. All right, so what I did there is I set result equal to null instead of checking if it was null. Thank you, JavaScript. A lot of languages won't let you do that sort of thing in there. But JavaScript definitely will. So, looks like I still got some problems here. So we smashed 8 and 7, added a new stone. So somehow here, I ended up with a wrong result. So that does look like there's a bug in my heap, which is unfortunate. I did test it for some simple use cases, but obviously not well enough. So let's look at what should have happened here. We smashed 8 and 7. So those got plugged off appropriately, and we tried to add a new stone, and it's this adding that didn't work. And it looks like it added to the appropriate spot where I expected. And then it percolated up and did a little swapperoni here. And that's where the undefined came from. So I'm thinking it's maybe the percolate up that was the problem. I think so. All right, so let's check that. How did we get undefined on percolate up? Index, Max-Heap.items at parent index. So I'm always looking at indexes less than me, so I should never have to worry about checking. Yeah, I think later today, Ryan, I'm actually thinking about doing maybe like 10 easy tree problems just to kind of get me back in touch with trees, because I definitely had a rough time with yesterday, and it was supposed to be an easy. Today is also supposed to be an easy. I think maybe they need some more levels. Just split things up a bit more. Max-Heap.items index. Items apparent index. All this is just looking like gobbledygook to me. Temp. And then we call Percolate up. So that looks good, actually. That looks good to me. So nothing glaringly obvious. I'll do a quick run through here. Left index, right index, and returning nothing otherwise. Okay, so I think the heap might be okay. Maybe. So I did take the new stone. That looked good. So what I'll do is I'll go ahead and print after we add the new stone. Let's see, max items dot, or max heap dot items. And I think even after we smash, I'll print that out too and just see, just kind of trying to narrow in on the problem so I don't waste a bunch of time looking at the wrong things. All right, so look at that. So I'm glad I checked this because this is not where I expected the error to be. So I smashed 8 and 7, which essentially ended up with me plucking 8. It should have done a percolate down, and then I plucked 7 and it should have done a percolate down. And somehow here I brought an item up that it shouldn't have been. So the problem, now we know, is in the percolate down. And since we didn't run into it on the first item, yeah, so just a real quick, like, kind of briefing on heaps. Heaps are almost generally associated with either a min heap or a max heap. And it's really good for keeping whatever your next biggest or next smallest number is. And the way it works is it's underneath, it's an array. But really, the way you think about it conceptually is more like a binary tree where each node has 2 children. And the 2 children are always either, depending if you're doing a mix, a min tree or a max, are always, one of them will always be the next value that you want on top. And so the biggest value always ends up in your 0th position for a max heap. And then you know that it's one of its children will always be the next biggest. So you can just take the biggest off and then do a small operation that does some swaps in place in your array, which is really memory efficient. We don't have to keep shrinking and growing an array and moving all the items. We know that we can just swap. And so the net of it is that plucking the biggest item out of an array becomes 0 of 1 operation, so constant time, plus the percolate down, which is log of n. So another way, removing the minimum or maximum item is log of n, and adding a new item anywhere is also going to be log of n. And the space complexity is going to just be n. So it's just good for finding mins. I think they're neat, but it's awkward. I'm sure I could have gotten the lines of code down. You know, I'm sure Wikipedia's got like a 20 line example, whatever, but I thought I had it right. But what I think happened here is that I think that maybe the not having a right child worked and not having a left child didn't, so I did a swap here when I shouldn't have. So I do check to see if the left index is greater than the max heap. Oh, look at that. I checked to see if it's greater than the length. It should be greater than or equal to the length. So I think that was probably it. So let's run this again. And yeah, I don't have a set time right now for doing problems. I'd like to get there, but I don't know when that's going to be. So I still do have some wrong answers, but it does look better. No more undefines. So in this case, I took 8 and 7, smashed them together, and I added a 1. So after smashing 8 and 7, we're down to 4, 2, 4, 1. And that's right. So what kind of talking about the heap, 4 is going to be my biggest value. And in either this one or that one will be my next biggest. So that's correct. When we add a new stone, we always add it to the end, and then we percolate it up. In this case, it's a really small number, so it doesn't involve any sort of percolation. So that was good. Now, smashing 4 and 4 is incorrect here. No, I'm sorry. That is correct. So what happened is I picked up the 4, and then I had to do a percolate down and basically said, okay, who's the next biggest, 2 or 4? It was 4, and so that's how I ended up getting 4 and 4. So here is the problem, though. When I smash those guys, I don't understand what the problem is actually. I think this worked like I expected, just the output's weird. I said smashing 4 and 4. So smashing 4 and 4 is correct. And then I console.logged the Max-Heap. And that's what I don't understand, is because I should have plucked this off. And I should have plucked this off. But what I'm seeing down here, it almost looks like it took off the 2 1s, which doesn't make any sense to me. So I did something wrong here. And I'm sure it's where I did that pop. That's the only place I know that would do an operation like this that would remove items from the end of the array. So basically what I did is when I pluck an item off the top, I grab the 0th item. I do the percolate down to do any sort of shuffling that needs to happen to maintain my heap. And at the end, I was always doing a pop in order to get rid of basically the end values, because they should have moved forward. And I believe that's correct. So it makes me wonder if the percolate down is what's wrong. This is so frustrating. This is programming for you, huh? I wish JavaScript just had like a native heap. Could have just been done. Save like 50 lines of code. That's correct. I believe this algorithm is correct. Let's look at our percolate down again. Take index, assuming I did the math correctly. Now we're checking properly if it's greater than the entire length, okay. Here we already had greater than length, greater than or equal to, or the left item is greater than that right item. And that all looks good to me. So what did I do wrong here? If the left index is... Alright, what we'll do is console log. And what I'll do is I'll say left index is bounds quitting. Don't forget to delete, or say to pop this. And then I'll put in the value here. And that should be Max-Heap dot items at Max-Heap dot items dot length -1. Okay. And here, if the right index is greater than the length, so there is no right child, or the left item is bigger than the right. So I'll say console.log and say swapping with left child. And I'll actually plug the values in here. So we only have to do this once. All right. And we'll do the same for the right. Okay, swapping index with right child. Okay, so lots of output this time. So we got 8741221. Swapping 8 with the left child. Okay, so this is basically how we got to this heap size there, which is fine. Okay, so here's the first actual operation. So we took 8 and 7, we smashed them together, we got 1. But when I look at my array here, somehow I have 2 4s. So at this point, we already did something wrong. Jeez. Now if I look at this, what I did here, I swapped 8 with the child, 7. Swapped 7 with a 2, left index is out of bounds, fine. Swapping 7 with right child, 4. So I swapped a 7 for a 4, which is fine. So, you know, essentially what I'm saying is here, I got rid of 8. I brought up the 7. This line is weird to me. Swapping 7 with right child 2. And I'm saying, hey, we should have got rid of the 1. All right, tell you what. What's up, Zach? Where the heck are you, man? 3 a.m.? 12 hours off? You in Oz right now? No, I don't. Oh, you got to be in like Swahili. And I hope you're having a great night. Staying safe. I'm just struggling with a heat problem. The problem is probably solved fine, and I just made some sort of dumb mistake with my actual heap. So tell you what, I think I've tortured you all long enough. Let's just look up the algorithm for Max-Heap. Complete binary tree in which the volume in each external node is greater than or equal to the values of the child. Okay. We'll check the math here. If a node is stored at index k, then its left child is 2k plus 1 and 2k plus 2. Do we get that right? That would have been up here. Two plus the index plus 1, 2. Okay, good. Okay, blah, blah, blah. Let's talk about percolation. Okay, start with the last node, swap with the current internal node with its large child, fine, and follow the swap node down. Okay. This really isn't helping me very much. So I guess I got the algorithm right. They're calling it SIFT. I've never heard it called SIFT before. Okay, well the good news is I think I got my heap algorithm correct. I think I just have a bug in it. Alright, so here is removing the max. The most common operation on a heap is deletion of the root. And the heap property is maintained by sifting down. Alright. This is what I call pluck. If number of vertices is 0, okay, fine. So we remove the top, or we get the top item. And this is kind of weird. They're always setting it to... Oh, I didn't do this. I did do the heap wrong. So I left a blank spot here, which was kind of weird. But what they did is they got the last item, brought it in, and then they swap. So let's do it that way. Okay, this is good. I messed up, sorry. When we remove we pluck items, what we do is we get the first item, that's going to be our biggest. Now what we do is we get the last item, which is it's probably one of the smaller ones. So it's a let's call it last item. It's equal to the last item in our array. And then we call percolate down. And percolate down is going to look a little bit different. So now we do have an item in here. So we have to make sure that we always swap with the appropriate item, and we can stop at some point too. So we're going to have another stop condition, I believe. So we got left and right correct. This is still good. So when it comes time to do the swap though, what we have to do is decide whether to go left or right. So what the deal is, we should always swap for whichever one is greater. So if the right index doesn't exist, or the left item is greater than the right, then we say swapping blah with left child, and we do that. But I also need to store a temp value, temp equal to my current item, because now we're doing a true swap. We're not just bringing it up. So we set u equal to the left, and then I need to set the now vacated spot with my temp variable, and then percolate again. And down here, that part's right. That part is almost right. We have to do the same thing. All right, temp equals right index. Awesome. Awesome. And then we just change this guy right here. And so this is really minor tweak to the algorithm, but that's what we got wrong. And so I didn't hit this before because I didn't do enough tests essentially, so that's a bummer. Okay, smashing 2 and 2 should have got, so we got the wrong answer again, but for a different reason. So let's look at what happened again. We got our array. It's close to sorted correctly, and it doesn't have to be sorted exactly correctly, so this is good. It's kind of hard to tell. I've got kind of too much logging going on. It's a little bit difficult. So something is still not right here. That's crazy. So we still have a problem here. So I'm going to clear out some of this logging. We'll get through this. Sorry, it's dragging on. Oh my gosh. So now what I'm doing is I'm saying that we got a problem in the pluck. So let's put a little log in here that lets us know when we're actually plucking. And we'll put the item in here. Okay. And when we percolate up, I'm not going to change any logging. But now we'll be able to see actually what's happening here. And so let me do one more log of the whole array. Max-Heap.items. Okay, so we'll actually see what this looks like at the beginning. And we'll do another one called plucked here at the end. Okay. And I think that logging was okay. Zach, you left me hanging. I want to know if you're in Swahili. All right. 274181. We get it roughly in order. That's good. So we pluck this. So this is what we started with. And if we come down here at the end, this is what we ended with. 1, 2, 3, 4, 5 elements. One, two, three, four, 5 elements. Oh, because I already removed one of them. So let me change my logging again. Sorry. Jeez. So let's do the plucking before we even start. Start changing anything. All right, so we've got our whole big array, 6 elements. We pluck 8. At the end of that pluck, we're down to 5 elements, 7, 2 and 4, 1 and 2. Okay, so that looks good to me. So we pluck this again. So at this point, I end up with the wrong answer. Look at that. Somehow I get 4 duplicated. So I plucked 7, which is correct. I swapped 7 with right child 4. That's not right. That is not right. Did I do that? When I plucked, I got the max value, which is 7, is the first item. My last item needs to be popped. So let's add this in here. Say moving this to the 0th position and percolate down. And that last item should have been a 2, not a 7. Okay, so like we did with the 8, when we plucked that 8, we grabbed the last item here, which was a 1. That's good. Moving to the 0, percolate down. That's good. That's good. Left index is out of bounds. Fine. Don't forget to pop this. I should remove that message. We don't have to do that anymore. So here it is at the end after plucked. We still have a bad answer. Look at that. Somehow we ended up with the second 2. What on earth is going wrong here? Look at this too. Swapping 8 with left child 2. Swapping 8 with right child. It shouldn't be the 8. Because the 8 should have been swapped in. What am I feel like I'm living in a strange world. Bizarro world. Ugh. I'm sorry this has been so frustrating. Thanks for sticking around. Okay. This is how it goes sometimes. Making the best of it. Cheers. Oh my gosh, look at that. I never I never moved the item up. I just talked about it. Okay. I don't have that last item variable anymore. That's fine. Let's try this one more time. This is the solution. Okay. Plucking. Moving 1 to the 0th position. Oh my gosh, it's still wrong. What on earth? Swapping 8 with left child. That's incorrect. Look at that, man. Max-Heap at 0. It's Max-Heap at dot items. Why did that even work? Did I do that anywhere else? Yeah, I sure did. That's so weird that that wasn't like a not compiler, interpreted error. Okay, there we go. Plucking 8, moving 1 to the 0th position. Percolate down, swapping 1 with 7, yes. 1 with 2, yes. Left index is out of bounds and we're quitting. And check it out. Somehow we still have 2 here. We got duplicate 2 still. So maybe there's another case where I did some logging for something and then didn't actually code it that way. So percolate down. Those were good. That's fine. I said max-heap.items at index equals the left index, and then the left index equals the temp, and then we check, so that should be fine. What about down here? Swapping with right child. Oh, yep, that's not right. Stupid bug. Index equals right index equals temp, and then swapped out. So I had the wrong item set to the temp variable, so it's getting duplicated. Okay, this is the last time. This is all correct now. Did we get the right answer? Yes. Yes, we did. It's a miracle. Okay, so now we have all this obnoxious logging. I'm going to go ahead and copy this stuff out there. I'm going to submit it, see if we solved the problem correctly. I think we did. Didn't really check some of those use cases. We got a wrong answer here. Input was 1 and 3, so I should have parsed it correctly. It's 3 and 1. Pluck 3 and 1. We pluck 3. We pluck 1. Okay. We smash 3 and 1 together. Okay, and then we added a new stone 2. But look, somehow we still had, so even though I plucked 1, somehow we ended up still having an item here. So I think I know what happened there. Ah, jeez. So this item here, what we did is we didn't account for there not being any items in here, or not being enough items. Oh, man. So when I plucked that one, I got the max value. And then I popped it. That's correct. Unless there's only one item in the array. If there's only one, then basically I take the same item out and put it right back in. So what should have happened there? I should only do this operation when It's just not very elegant. Basically, I always need to pop. So let's just do that. Okay, so we always need to reduce by 1. But if Max-Heap dot length equals 0, or we'll say greater than 0, that's when we put the item back on. And if the max length is 0, then we don't need to percolate down. There's nothing to percolate. So that will prevent us from re-adding the same items to the list. Got a runtime error. Too many equal signs. Oh, my screen went weird. Not sure what happened there. Okay, so where was it? It's like a snake. Oh, scroll too far. There we go. Oh my gosh, you still awake out there? I am almost not awake. Scroll that. So we got our same back, no, we got the wrong answer. What on earth is happening here? So we had this big mess. We plucked the item. Didn't get duplicated. That actually looks good. This is all wrong. I plucked the 8, but then I never removed it. Well, let's look at that again. I got the max value correctly. That was the 8. The last value equals. I should have written some unit tests for my heap here. That would save me all the trouble in the world. We have yet to see an actual problem with the algorithm for the problem. It's all just been this stupid heap. So we do remove the last item. Man, I did it again. It's the same error. It's not Max-Heap. This is why reason number 20 why JavaScript is not a great language for coding challenges. It lets you do stuff that doesn't make sense. It lets you access things as arrays that aren't arrays. And it won't yell at you. It'll just behave in strange ways. So now I think we're good. I'm going to go ahead and run that sample case that broke us before, this 1 and 3. I'm going to go ahead and do that as custom input. See if we get the right answer here. Okay, the code is finished. Did we get the right answer though? No. Oh my gosh. I'm about 2 seconds. I'm just finding someone else who did a heap and just dropping it in here. Plucked 3 and 1. Okay. That's not correct. I shouldn't have had 1 left over. After I got the 3 and the 1, I should have had nothing left. I should have just pushed the 2. So it's still in that same area here. I'll always pop. So always remove the last element from the array. Look, I did greater than or equal to 0. Man. This time it's going to work. I'm so sorry this took so long. I'm sorry if you stuck around and were disappointed. This is the solution. Alright, let's try submitting it and then I'll clean this stuff up and we'll see how the runtime was. What? How on earth did we get -5? 10, 10, 7, and 2. 10, 10. We got 2 and 7. That's not correct. Let's look at this a little closer. So we got 10, 10, 7, and 2. We plucked the 10. We moved the 2 up. That's fine. We did percolate down. We swapped 2 with the bigger child, 10. Great. Left index is done. Okay, so now we're down to 10, 2, 7. That's fine. We plucked the 10. We moved the last element up. Percolate down. We swapped 7 with left child, 2. That's not right. Because 7 is bigger. So, what I think should have happened here is we've got a condition here that checks the length for the right index. We say if this or this, and so we're hitting that other condition that causes us to do a bad swap. So what it should do is only check if left is greater than right. But down here, I should only try to do this if right index is less than if the right index is less than or equal to the length minus 1. Yeah, I'll do that, RazTubes. If you get benched, uh-oh, is that like laid off, or are you like a pro basketball player? I think I did add these to a playlist, actually. We'll check that in a second here. And later tonight, I'm thinking about doing like 10 tree problems, just because obviously I'm struggling with them. So do we get the right answer there? Okay, cool. So now I'm going to take this sample input to Baruchus, and we'll try this here. It always scares me when I see wrong answer, but that's from our prior submission. Okay, so we got some answers here. The 2 and the 7 are in the correct order. Awesome. Okay, adding new stone 5. Answer is 5, expected 5. Okay. Now, let's try the other one we had a problem with. 1 and 3. If that still works, we'll go ahead and submit again. Alright, we got it. So, I'm feeling pretty good. Gonna submit. I feel like we've got a good solution. It is n, log n. So I wouldn't be surprised to see that somebody figured out how to do this in constant time. Or, sorry, not constant. That'd be amazing. Someone figured out how to do it in linear time, O of n. Oh my gosh, we got the wrong answer again. Let's see what happened here. I guess I could just scroll down and see it. Okay. We got 10, 9, 2, 3. We're finding like every problem in my freaking heap. I should put this heap up on NPM afterwards. Battle hardened. 10, 9, 2, 3. We pluck the 10. How do things work afterwards? That's incorrect. Oh my gosh. The 2 should not be at the top there. It should be that 9. So we're having a problem with our percolate down. So we got the 10 out. That's good. We moved the 3 up to the 0th position. That's correct. We swapped 3 with a left child of 9. Boom. Then we're out of children to check, so we're good. But then this happened. Oh my god. Okay. Look at this. Look at what I did. Oh my gosh, that hurts. I didn't do an else if. I changed it from else. I meant to do else if. Wow. Okay. Oh, geez. Let's run this code. This has been the most ridiculous problem for me. And all just because I thought I'd be slick and do a Max-Heap from memory. So there was the input. Still got the wrong answer. 10, 9, 2, 3. Pluck the 10. Swap. That looks good. Now we got 9, 3, 2 left. That's good. We did a pluck. Got the 9. We moved the last item to the 0th position. Good. And this is our result afterwards. Not good. This percolate down should have saw that the 3 was bigger than the 2. So in this case, it was another case where I've got a left child but no right child. What should have happened here, though, is I should have seen that my left child was bigger than the top. And this happened in percolate down. Max heap's length was greater than 0. So in percolate down, I should have said, is my left index, yes, greater than my right index? Oh my gosh. I didn't check to see if it was bigger than me. Nowhere in this algorithm am I ever checking to see if it's bigger than me. I'm only checking to see which one's bigger, left or right. Okay, so what I should do is check to see what do I do here? If the left index is greater than the max heap dot items at index. So is it greater than me? And it's greater than the right index. Then we swap. Else, if the right index is within bounds and the max heap dot items at right index is greater than me. Does that solve our problem? Let's see. So I got the sample in there. We run the code. We could pretty much just look at the output here of what's being plucked and see that no, it's not right. What did I do? 932. Pluck 9, we move the 2 to the top. And then I just get no output. So what does it look like here? At this point we've got 2 and 3. For whatever reason, it's just stopping there. Move the 2 to the 0th and then percolate down. So if we go look at this percolate down, I log if that's the condition. So what happens is I didn't hit either of these items and it just fell through the bottom. Max heap dot items at left index is greater than max heap dot items at right index. We've got a 2 and a 3. So right now my index has a value of 2, and my left index has a value of 3. Okay, so I'm saying is 3 greater than 2 and oh my gosh. Wow. here's the problem. And I'm saying is 3 greater than undefined. Man. So that's a problem. This if is getting out of control though, so I don't want to just trim that out in too ugly a way. It just doesn't feel right. I'm checking too many things here. Max-Heaps. So, I mean, what I need to do is basically add a length check here. Ugh. I already have the length check down here. So in this case, we had a 2 at the top, and I'm looking at a 3. And I think what should have happened is I should have left this check up there earlier. So it's basically going to be if this and this or this. But man, that is just not, that is not code that I'm proud of. Like, oh man, I don't even know how to make this look intelligible. So if this and this or this, that's weird. I keep typing. There it goes. Okay. All right. I believe that's the solution now. If I was at an interview, the interviewer would have definitely fallen asleep by now or just kicked me out. Or if I was doing it on a whiteboard, they probably would have not have noticed all the little mistakes I made that led us to here. Did I not click run? Okay. Still wrong. What on earth is happening here? We know it's that one line, like that one area, and percolate down that's the problem. If the max heap is, if the left item, which in this case is a 3, is greater than 2, yes. And the right index, oh my gosh, I have that sign the wrong way, is greater than or equal to, I can actually just say the length, or the left item is bigger than the right item. So what did I change here exactly? Okay, I had the wrong sign direction. Man, I thought I was going to do like 10 tree problems, but now I don't want to look at another tree for a while. So I got the right answer that time. And let's look. And yeah, so I see, yeah, pluck the 9. Here was the problem we had. It wasn't swapping, but now it is. So our order ended up being 3 and 2. So now if we submit, we should be right. I can't imagine there being another problem. All right, we got it. I'm going to remove the consoles. Hooray. Thank you so much for sticking around. Ugh. It does not like me doing Control F. It keeps bringing that menu up whenever I do that. It's weird. Is it the control button? Ugh, and it doesn't like when I do the end key. So we're just going to drag it out to code. All right, console dot. I have no more consoles. Oh, several consoles. All right. Could have regexed it, but I didn't. So I'll be curious to see if anyone else did a heap. You know, I didn't even really consider other solutions. So maybe there's a better way to do this, but I don't know. I'm pretty happy with it. So let's go check out the details and see how we did. So not great. We were n log n, so we knew that there was a chance that there's somebody out there that figured out how to do it in n. They don't have enough submissions to show the memory distribution. That's a shame. So I thought we did a good job there. So let's see. So if we look at sample solutions for what we did. Oh my god. So that's depressing. So they basically did the straightforward approach and performed just as well, where they basically just followed the rules and just did exactly what the problem said to do without any sort of heap or anything. So it took me like 60 lines to get the same performance as this. So that's embarrassing. And basically all they do is they just sort, grab the first two, and then interject that item. And then when they're done, they return the end there. Wow. So for all my code, that's where I ended up. What else we got? So again, they're just sorting on every iteration, which is not something I wanted to do. And what's crazy to me is, I mean, unless I'm missing something, the runtime of this should technically be much worse than mine, because they are going through n items, and oh, actually this one's better. But in the other solution that like ran at the same time as mine, that's n operations, and then they're sorting, which is n log n. So this algorithm should be n squared log n, and yet it performed the same in practice, probably because this list was very close to being sorted, so that n log n in practice ended up being much shorter. So this is a case where I think that Big O let me down, and that's a shame. So let's look at the very leftmost here and see what happened here. So the very best solution. Wow, look at that. Another one where it's n squared. So they literally loop through this whole array. And they could potentially end up looping more than once per item because of how it reduces. And then they just find the biggest item. And so that's crazy to me. So that's n squared again. Oh, really? Good to know, Ryan. Okay. Good to know. Because, yeah, that's a little disheartening to think that, like, I believe I did the runtime correctly. I believe my algorithm was n log n, and here it is performing less than an n squared, poorer than an n squared algorithm. So, whatever. I'm okay with it. And I'm not okay with how much code I wrote to do it. So, c'est la vie. Thanks for sticking around. And before I go, I will go ahead and check to see. Hey, look at this. If we looked at the hint, it says we can do it in a heap or by sorting some stones. So if I had seen that hint, I probably still would have gone with the heap just for fun. So I don't feel too bad. But I did want to go ahead and show you on YouTube. I think that I created a playlist for all these problems if for some reason you wanted to punish yourself. So we go to playlists, and oh, I don't. Okay, so let's fix that right now. We're gonna get this settled on air, real time. So did you say you did this one, Ryan? Okay, and if we go over to, you know, it's gonna take me a minute to do it. Oh, look, so here's the deal. I created a LeetCoding problem. I didn't add any problems to it. I didn't add any videos. Okay, so I'll get that added off air. And spare y'all. I've already been on for almost 2 hours. But yeah, Ryan, I don't know if you can send me your solutions or anything, but I'd like to see how you're doing it. Anyway, I'll catch you on the flip side.